Okay. Okay, hello, welcome everybody. Okay, so this is our second class in advanced math. So we have two new assignments. So you have these two are due on May 26th. So this is functions and models, revenue, profit, and break even. And the other is 4 ways to represent a function. Okay, does anybody have any questions before we start? Oh, I'm sorry. I didn't share my screen just then, did I? Sorry about that. Let me try that again. Let's try that again. Here. Okay, let me show you that again. Okay, sorry about that. We have 2 new homework due on May 26th. So this one about break even, and this one called 4 ways to represent a function. So, okay, now, does anybody have any questions before we start? So I think I sent everyone an email about how to purchase the book. Okay, somebody had some questions about the previous homework. Okay, I guess we can do that. And also, but I sent you through Manaba something about how to purchase the book. And it looks like you can't actually enter your access code into WebAssign until approximately the 26th day. I guess there'll be a pop-up message for you to enter it. But that won't appear, I think, until about the 26th. So, and then they also gave us some kind of warning about, like, after you enter that, there could be approximately a 24-hour period where you won't have access to WebAssign. So that's kind of annoying, but I don't know exactly what's going on there. But so hopefully that should help you understand what's going on as much as I understand it. Okay, anybody have other questions? Okay, let's see what we have here. Advanced math, supply and demand. Let's look at that. Okay, which question did you have a question about? Can I turn on your mic? I think you can turn on your mic.
Okay, sir.
Yeah.
I have a question regarding the question number 8. So I followed your, no, actually I followed the website's steps to determining shortage or surplus. It's demand minus supply.
This one here?
Yeah, question number 8.
This is number 8, right? Can you see my screen?
Yes.
Okay, yes.
So I tried to determine whether it has a shortage or surplus by subtracting demand and supply. So,
Okay.
and I found that the result is negative. So does that mean it's actually should be a surplus? But the correct answer is shortage. So that's what I don't get.
Okay, let me read this. I'm not quite up to speed on this one, so let me read it. So it says the demand for monorail service can be approximated by this. So this is the demand function, right? And where P is what? P is the fare, P is the price, and P is between 3 and 8. Okay, so the price is, yeah. Okay, so the price is between 3 and 8. So this is, assume the cooperative is prepared to provide service for this many million rides per day, okay, at a fare of this, okay. Calculate the equilibrium price and equilibrium demand. Okay, so did you get that part?
Yeah, I get that one, yeah.
Okay, good. Okay, next part is graph the demand and supply functions to confirm your answer. Okay, so I didn't do this, but I can at least see that this one is downward sloping, right? In other words, as P increases, Q will decrease, right? And this one is upward sloping. So it's probably not going to be this one because both of these are downward. Might be this one. It might be this one. It's probably not this one. So we can say it's between one of these two. And then the difference between the two is that here the downward sloping one is not linear. And here the downward sloping one is linear. So which one is downward sloping? This one. And and that's not linear. This one is upward sloping and this is linear. So the downward sloping one is not linear, so it must be A. Or this one rather, it must be this one. And B, what do they call this? They don't have it, just anyway, it must be this one. Okay, now, estimate the shortage or surplus. What does that say? Estimate the at the December fare of 7 of these things per ride. Okay, so first of all, it looks like, I guess it looks like this. Is that what we said? Yeah, looks like this. And 7 is right here, right? Do you agree with that?
Yeah, I agree.
Okay, so 7 is here. So the, which is the supply? I guess the supply is the upward sloping one. So the supply is greater than the demand. Do you agree with that?
Yes.
Okay, so there should be a surplus, right?
Yes.
And you say it said that there should be you say the answer was shortage?
Yeah.
Okay, let me check that. Let me check that. Okay, this is supply and demand number 8. Yeah, that's strange. Anybody else have that same issue?
I also have the same issue.
What?
I also have the same issue. The same question.
Okay. Where is it now? I lost it. Here it is. No. Here it is. Okay, let's check that once more. So number 8. So this is, well, yeah. So I guess the other way to do this is to put 7 into here and put 7 into here. Did you do that?
Excuse me?
The person who asked the question, did you put 7 into here and into here?
Yeah. I did that.
Okay. And when you did that, and then you subtracted, this one is the demand. So the demand was lower, supposedly. So when you subtracted, what did you do? Subtract the demand from the, take demand and subtract supply from it, or vice versa?
I subtract supply from demand.
Supply. So you did this one, the bottom one, minus the, I'm sorry, say that again?
Sorry, demand minus supply, basically, yeah.
You took this one minus this one.
Yeah.
Okay, so then that should be positive. Did you get positive? Sorry, that should be negative. Did you get negative?
Yeah, it's a negative.
Oh, that's odd. Anybody else have this issue? So the demand was negative. So that was negative. So the supply is, oh wait, sorry, you did what? You took the demand minus this one and you got positive or negative?
I got negative.
Okay, so if you did this one minus that one, you get positive, yeah. So supply is higher. Okay. I'm not sure, to be honest. Looks like what you did is right. Anybody else have an issue with this?
Yes, we all have the same issues.
Oh, good. Okay, we all had the same issue. Okay, then at least we're all thinking the same way. I think there's some problem here. So I think the answer should be, there should be a surplus. There would be a surplus, and the amount is, what was the number that you came up with when you subtracted?
For mine, it's 3 million
3,
rice
right,
per day.
yeah. Okay, well, it looks to me like it should be the other way around. It should be 3, but it should be a surplus. So I'll look into it a little bit further, but looks like you're on the right track. So I'm sorry if the system is wrong.
Thank you, Professor.
Okay. Anybody else? Okay. Then let's go on to something else. Let's go on to this topic here, 4 ways to represent a function. So let's talk about this. Everybody see my screen?
Yes.
Okay. So here we have a couple different examples of where we might use a function. First one is the area of a circle depends on the radius. So they say a function arises whenever one quantity depends on another. So here we have the area depends on the radius, and everybody knows the formula is the area equals pi r squared. So that's the explicit way that area depends on radius. But anyway, in any case, we know that area depends on radius. Where with each positive number r, there is a single value of a. Okay. Next one is human population, p, the world population p, depends on time. Okay, so for example, if you put in 1950, at that time, there were about 2.5 billion people. Okay, so if you put in a different time, you get a different population. Okay, so, okay, next one. The cost of mailing a first-class letter depends on the weight of the letter. Although there's no simple formula that connects W and C, the post office has a rule for determining C when W is known. Okay, one more example. The vertical acceleration of the ground as measured by a seismograph during an earthquake is a function of the time. Figure 1 shows a graph generated by the seismic activity during the Northridge earthquake that shook Los Angeles in 1994. So for a given t, the graph provides the corresponding value of A. What does A stand for? What does A stand for?
Vertical acceleration.
Vertical acceleration. So normally we don't think of the ground as accelerating, right? We don't think of the ground as accelerating vertically, right? Does everyone agree with that normally?
Yeah.
But I guess during an earthquake, since the ground is moving, we could say that if it's going from 0 to some speed, it must accelerate. So, and this is a plot of that. Okay, is this clear? Okay, now, what is a function? A function f is a rule that assigns to each element x in one set, D, to exactly one element in another set called E. How many people have seen this definition before? Raise your hand. Only 2 people? 3? 5? Oh, by the way, okay, yeah, we'll take a break in a minute. Okay, so what do we usually call this thing D, and what do we usually call E?
E is domain.
Right. D is the domain, and
And
E is called the range. And the elements in D, well, no, sorry, I don't want to say that. So that's the definition of a function. So let's read it. We usually consider functions for which the sets D and E are real numbers, but they don't have to be real numbers. So for example, let me see if I can write something here. Let's take one set D and another set E. Now usually, like in this example, y equals x squared, then we know that 2, and if suppose we have 2 and 5 and 8 in this set D, then 2 so we know that 2 gets associated with 4, and 5 gets associated with 25, and 8 gets associated with 64, right? So this is normally with, when we have numbers, we have this kind of picture, but we don't have to have numbers. We could have something like this. And this could be So these are not all numbers, there are some numbers there. And then we could have like this, and we can have like that, and that, and that, for example. Okay, now for this picture, let's call this picture F, and let's call this picture G. And so we would write F of 2 equals what? 4, right? And F of 5 equals 25. For G, we could write G of star equals what? 9. And G of A equals what? Question mark, right? Okay, do you everyone understand this?
Yes.
And also, we use the following language. We say the image of star under G is 9. And then we could say the image of A under G is what? Is question mark. And we could say the image of 7 under G is what?
Z.
Z. Okay, so we can use this word image like that. We also say G of A equals question mark. G of star equals 9. So going back to here. So what is the domain for G? This is the domain, and this is the range. So usually we write the domain in set notation. So I would say the domain is that, comma, A, comma, 7. Okay? Okay, and the range of F is the set of all possible values of f of x as x varies throughout the domain. So one thing here is that I almost always forget is, suppose we had a few more values here. Suppose we had like t in here and one more, say, 8. Okay, now there's no element in D that gets sent to 8. 7 gets sent to Z, A gets sent to question mark, star to 9, and this thing gets sent to the square. There's nothing that gets sent to T, and there's nothing that gets sent to 8. So if 8 and T are in this set, then we call that set not the range, we call it the codomain. Okay? But the range is just the set of things that actually get hit by elements from here. Okay, the range, so the codomain, I guess, could be bigger than the range, but the range is the set of things that actually get hit. Okay, is there any question about that? Okay, and then a symbol that represents a number in the range of f is called the dependent variable. And a symbol and the arbitrary elements in the domain are represented by the independent variable. So normally we write something like this. Y equals f of x, and x is the independent variable, and the dependent variable is y. Any questions about that? Okay, now another way to think of a function besides this definition, so we could talk about this definition here. We just talked about that. But another way is to think of a function as a machine, like this. So we put something into the machine, into the function, and we get something out. Okay, so we put an input in, we get an output out. So that's another way to think about what a function is. Okay, and then we have this picture, which I just drew. This is another way. They call it an arrow diagram. So this says that x goes to f of x, a goes to f of a, and this goes to something. Does everyone understand how, let me go back to here. I used the word image. So suppose this function is f. I can say, what is the image of 2 under f? What's the answer to that? Anybody?
4.
Yeah, the image of 2 under f is 4. And we can write that, we said, as f of 2 equals 4. Does everyone agree with that?
Yes.
So if I make a general picture, and I have the function f, and I have an element a here, what can I say is the image of a? How can I name the image of a?
FA.
FA.
F of a. Okay, good. Okay, good. All right, let's go on. Okay, the next thing we want to talk about is, or there's one other way to describe a function.
This is pretty interesting. It says on Wikipedia that a
What the
cockroach
hell
can
is
hold
that?
its breath for 40 minutes.
The hell is that? My phone started talking to me. Excuse me. Okay, so another way to describe a function is by a graph. So, for example, of course, we could say, to kind of describe a function like that. So maybe that's, maybe I'm trying to draw this. But anyway, this also tells me how the function behaves. Or it tells me, like, if I want to know what 2 gets mapped to, I can just go up to here and figure out what the height is, and that will tell me f of 2, or what that will tell me what 2 gets mapped to. Okay, so they say the most common method for visualizing a function, is its graph. If f is a function with domain D, then what do we mean by the graph? Well, we mean this, but how do we write that? We write it like this. This means the set of all x comma f of x. That's the set of all ordered pairs where x is in the domain. Does that make sense to everyone? Or should I explain that further? Okay. Okay, so let's go on. The graph of a function f gives us a useful picture of the behavior. Okay, well, we know about this. Let's look at this picture here. So here's the graph. It's in red. So what's the domain of this curve, of this function? It's the set of inputs for where this function is defined. Whoops, I didn't mean to do that. See if I can undo that. No, I can't. Can I erase it? Yeah, okay. Oh well. Okay, let me try this again. So this is the domain. And what is the range? It's the set of heights that get mapped from the domain. So it's actually right here. So this is the range. Any questions about that? Okay, so if we have this figure here, what is f of 1? What is f of 1?
Is 3?
So I guess here, what's this? This is 0 here. 1, 2, 3, 4 maybe? Oh, sorry, f of 1 is here. So it's 3 maybe? Yeah, f of 1 is 3. And what is f of 5? 2, 3, 4, 5. Well, that's hard to say, right? F of 5 is somewhere around here. Okay. Okay, let's try something else. Let's look at example 3. Suppose we have this function defined like that. And suppose we have some h, which is just some number, some constant. They ask us, what is this? So let's talk about that. If we have, wait a second. Okay, let's try this. Let's look at, okay, just quickly, suppose we have f of x equals a squared plus 3. What's f of 1?
1 squared plus 3.
1 squared plus 3. What's f of 2? 2 squared plus 3, right? What's f of 5?
5 squared plus 3.
5 squared plus 3, good. Okay, so what's f of a? So whatever, oh, sorry, not, wait a second, sorry. What's that? Sorry about that. It should be x. Okay. X squared plus 3, sorry about that. Okay, what is f of a?
A squared plus 3.
Okay, what is f of b?
B squared plus 3.
Right. And then what is f of a plus b?
A plus B squared plus 3.
So whatever we put into here, we're supposed to square it and then add 3. So now we're putting in this, a plus b, so we're supposed to square that and add 3. So that's a plus b, f of a plus b. What's f of a plus b plus c?
A plus B plus C squared plus 3.
Okay. Now suppose we have another function, g of x equals x plus 8. Okay? So everyone understand this is g. Okay, and we just finished. What is f of a plus b? We said it's a plus b squared plus 3. What is f of a plus b plus c? It's a plus b plus c squared plus 3. So what about if we say, what's this? So not a plus b plus c, but g. So what's the answer?
X
X plus
B
X
squared
squared.
plus 3.
So again, whatever we put into f, we're supposed to square it. So I should square this and then add 3. So, but what is g? I can just replace g by this if I want. So I get x plus 8 squared plus 3. Okay? Everyone understand that?
Yes.
Now, this has a special notation. When we put one function inside another function, I'm putting g inside of f, there's a special notation for this. Anybody know what it is? It's called f circle g. Okay? And it has a name also. It's called the composition of f and g. And we write it like this. We write it like that. Okay, the composition of f and g is f of g, and we write it f circle g. Okay, now, here's a question. What about that? Is that true or not true? So we just did this one. What was this again? F circle G is what?
X plus A squared plus
We
3.
just did it there. So it's x plus 8 squared plus 3. Now we have to do this one. So G is x plus 8. So this means that means that. So that means putting F into G. So G is here. So I have to put F in there. That means just replace X by F. So I do this. Instead of X, I put in, instead of this X, I write F, and then I have to add 8. So I get that. But what was F? I think it was X squared plus 3, and then I have to add 8. So what do I get? X squared plus 11. So, are they equal?
No, they're not.
No.
No. No, they're not equal. definitely, I mean, pretty clearly it's not, they're not equal. So is this true?
No, it's not.
Oh, no, it's not.
Okay. So, you know, we're you know, in arithmetic, we can say 2 plus 4 equals 4 plus 2, right? We're allowed to switch the order there, right?
Yes.
And we're allowed to do the same thing with multiplication. 2 times 3 is equal to 3 times 2, right? But we're not allowed to do that with subtraction. 2 minus 4 is not equal to 4 minus 2. And we're not allowed to do that with division either. 2 divided by 4 is not equal to 4 divided by 2. And here, are we allowed to switch the order here? No.
No.
Okay? So we can't switch the order for this one, just like we can't switch the orders for these. Everyone understand that?
Yes.
Okay. So, and what is this called when we do this? When we do this thing here? What is that
Composition.
called?
Composition of function.
Yeah, composition of functions or composition of f and g. Or you can say f composition g. Anyway, the composition of f and g. Okay? So composition, you can't switch the order. Cannot switch the order. Okay. Okay, now let's go back to here. So let's, maybe I should take a picture of this. And put it in here, if I can. Maybe I can't. Here. No, it didn't work. Why not? Well, seems like you should be able to paste in here. By the way, how many people have used this application, OneNote? How many people have used this application? 6 people. Okay. It's kind of a fun application. I'll just show you a few little tricks that I discovered in the last week or so. First of all, if you want to draw a nice graph, of course, not so important, but you can use this and you can do that. So that's easy. And also, this is kind of fun. If you do, you can say, let's see if I can write this well. The composition of f and g is not I don't think this is going to work, the same as, okay, let's just see how well this works. So if I go here, let's see how that works. Okay, and then click here. No, it didn't work. Anyway, it's supposed to turn it into letters, but that didn't work too well. But what does work usually is if you go 2x plus 3y equals 7, and then you do the same thing, you circle here, and then you go here, it worked. So 2x plus 3y equals 7, and then you can do things like this. You can solve for x, for example, and it gives you that. And if there are more, oh, here, and it shows you the steps if you want to. You can see them like that. It tells you how to do it. Okay, so that's kind of fun. And then also, you can do this. Graph it in 2D. So it gives you the graph. And if you want to do a different graph, for example, you go y equals e to the x. Again, you circle it. And you can do that. And then again, you can graph it. Okay? Anyway, that's kind of fun. I just discovered that in the last week or so. Okay, so anyway, I was trying to paste something in here, but I wasn't able to. I don't know why. Copy it and try to paste it again. Paste. Okay, there it is. Okay, so let's look at this. So what is this going to be if this is f? So what we need to do is we need to calculate f of a plus h. So that's going to be what? 2 times a plus h squared minus 5 times a plus h plus 1. And then we also need to calculate this part, f of a. And that's, we already basically have that already, 2a squared, sorry, minus, I guess I can erase here, let's see, erase. Okay, 2a squared minus 5a, I don't know why that happened, plus 1. And so we want to take this one minus this one, so that will be the top part here. And then we just want to divide that by h. So, and that's what we'll get if we do this. Does anybody have any questions about that? Is that clear? Okay. So let's go back to here. So that's what they do. They do f of x plus h. They get this. They simplify it a bit here. And then they subtract this one. And they do all of this. And then they do a little simplification, a little bit more simplification here. Then they see that all the terms have an h. They cancel out the h, and we finally end up with that. Anybody have any questions about how to do that? Okay. Okay, let's look at okay, let's look at this one. This is the we said that here we said that a is a function of r. What does that mean? That means that the area depends on r. And the actual formula was this. So they say the most useful representation of the area of a circle as a function of its radius is to use the formula. So we could use other representations. We talked about 4 representations of a function. We talked about the definition. They're calling the verbal definition. We talked about we talk about a table of values. We talk about a graph, and we can talk about an explicit formula. So here, the best way to explain this, the area as a function of its radius, is using this formula. However, in this case, we want the population as a function of time. There's probably no formula that's going to give you exactly the population as a function of time. So it's better, it might be better to just present it like this. So this tells you in 1900, this was the population. In 1970, this was the population. In 2000, this was the population. So there's probably no formula that's going to give you this or this whole thing. So anyway, but this is a representation of the function. Does everyone agree with that? Any questions about that? Okay, so let's see. So they say another thing we could do is to plot these values. And they say that's figure 9. So that's here. So this and this are exactly the same. In other words, like if you want to know 1920, you get this height. And if you could read this off, you would see that 1920 is 1860. So this plot or this scatter plot gives us exactly the same information that this does. So either one of these will represent the function, either this or this. Okay, any questions about that? Now, what is this picture here? Yeah, you don't have to raise your hand, you can just speak. Go ahead. Yeah, you don't have to raise your hand, you can just speak. Just unmute your microphone and speak. What is this picture here?
It's a graph.
It's a graph. It is a graph, it's true. How does it differ from the picture on the left?
Uh, there's no best fit line.
So, I'm sorry, could you say that again?
There's no best fit line on the left graph.
There's no what kind of line? Sorry.
Best fit curve or line.
Best fit, right.
Yeah.
Yeah, there's no best fit. So he's talking about this red line here and calling that the line of best fit. So yeah, that's right. So which is the actual function? Is it the blue dots? Or is it the red line? Which one, this one or this one, which is the actual function?
The red line.
Okay, let's have a poll. Let's see, how do I do this? Poll. Okay, here. So, what in the world is that? I'll edit it. Okay, let's have a vote. Which is the function, the red line or the blue dots? Which is the actual function? I should have wrote, which is the actual function. But anyway, I'll just leave it the way I wrote it. Okay, let's check the poll. So I'll end it. And let's share it. Okay, so the question was, let's see, which is the actual, I should have put it, stress the word, should have written the word actual, I said actual. Which is the actual function? So we got 62% said red and 38% said blue. And who was right? The blue. So the red is not the actual function. It wasn't the actual data. The actual data is the blue. So that was the original data, the original function. What's the red? What is the red doing there? Well, he called it the line of best fit. And it's just like an approximation of the blue dots. Okay? It's an approximation of the blue dots. And the formula that they use to generate that red line is up here. What kind of function or formula is this? What kind of function is that? What kind of function is that?
Increasing function.
Definitely increasing, that's true. What else?
Exponential.
What else can you say besides increasing? Why can't I do it this time? I was able to do it before. Okay. Okay, what kind of function is this here?
Exponential function.
What kind?
Exponential.
Yes, it is an exponential function. What did she say it was?
Oh,
She said it was
exponential.
it's an exponential function. I think we just saw an exponential function when I was playing around with this thing here. Let's try it again. I think everybody knows this one. See if I can get this working. Why doesn't this work? I have to do that. It's pretty confusing, actually, to get all this working. It's still not working. Try this. Okay, y equals e to the x. That is also called exponential. What does the graph of this look like? Well, fortunately, I have this. It didn't work that time. Didn't like my writing. Let me try it again. Make it a little bit bigger. Try it again. Y equals e to the x. Maybe, let's see if it likes that. Okay, let's try it again. Nope. Doesn't like my writing anymore. It didn't mind it before, but now it doesn't like it. All right, once more. Oops. Hopelessly difficult to use this actually. Y equals e to the x. Let's try it once more. And let's try that once more. Okay, there. Okay, so this is an exponential function that probably you're familiar with. And we did do the graph of it. And it looks like that. Now, let's insert that on the page. Okay, that was cute. And so is this an exponential function? What does this function and this function, what do they have in common?
Variable power.
What?
Variable power.
Okay, can't hear it. Can you say it again?
They both have variable power.
Variable powers. Okay, so, okay, can somebody else give me the same answer again? What do they have in common? What do these two, this one and this one, have in common?
They are power of a constant.
What?
Power of a constant.
Power of a constant?
Yeah. Is it?
What do you mean by that?
Because E is a constant and you have
Ah,
constant in
okay,
the
okay.
function.
Yeah, okay. I want somebody to say it a little bit differently. Try again. Somebody else try again. What do these two have in common? Okay, let me rewrite this. This is f of x, right? Is everyone, right? Everyone agree with that? Like usually we write f of x here, right? Okay, anybody want to say it? What do these have in common? This and this. I think one person said it at the beginning, but I want somebody else to say it a little bit, or say it again. Okay, well, anyway, I'll do that in a minute, but let me do one thing. Let's see, let me do one thing. And that is, let me do something here. Okay. Okay, so let me ask again, now that everybody's woke up a little bit. Some people, you can turn off your video. You don't have to turn it on anymore. What do these two have in common? They're both, I say that they're both exponential functions. This one and this one. So why is that? What do I mean by exponential functions? Okay, somebody said it correctly, but the thing is, what's the variable for this function? What's the independent variable for this function?
X.
What is
X.
it? X, right? What's the independent variable for this function?
It's T.
T. Where is X in this function? Up here, right? It's in the exponent, right? It's not, we're not talking about this function, x squared, where x is down here. We're talking about e to the x. So x is up here in the exponent. Okay, what about this? This function is a function of, the independent variable is t. Where is t in this function? It's also in the exponent. That's what makes a function an exponential function. If the variable is in the exponent. What that does is it makes the function grow really fast, like this. This is growing really fast, much more quickly than this, much more quickly than that. So does anybody remember any time recently when you've heard about exponential functions? Anybody remember that from any recent discussions? No? Nobody
The
remembers?
situation nowadays.
What?
Do you mean like real life situation?
I'm sorry, can't hear, sorry. Maybe my speaker's not on loud enough. Say it again?
By example, do you mean real life situation?
Oh, real life situation, yes.
Is it the coronavirus
Yeah,
situation that
yeah,
we're talking about?
right. I remember when school was closing last semester, I remember I started to look at the coronavirus in middle of January in China, and I was super shocked because the numbers, when you looked at them, were growing exponentially, super fast. So exponential functions that grow, quantities that grow exponentially, they have what's called a doubling time. Doubling time means if the number of number of cases was, say, 5,000 today, if the doubling time is 3 days, then what does that mean?
3 days, it should be double.
Yeah, in 3 days, it's going to be double, 10,000.
Yeah.
And then what does that mean? The next 3 days, then what?
Doubles again.
Again, double.
So what will it be? So today it's 5,000. Today is the 19th of May. So on the 22nd, it's going to be what?
10K.
10,000. And then what? On the 25th, it's going to be what?
20,000.
20,000. And on the 28th, it's going to be what?
40,000.
And then on the 31st, it's going to be what? I don't know. The 31 days in May, I'm not sure. But anyway, on the 31st, what's it going to be?
80,000.
80,000, right?
Yeah.
80,000. How many days was that? From 31 to today, we said it started at 5,000. And then what? This is how many days? 12 days, right?
Yeah.
12 days. In 12 days, if the doubling rate is 3 days, And exponential quantities that grow exponentially, that is, quantities that have exponential growth, have a doubling rate. So it might not be 3 days, could be 4 days, could be 2 days, could be 10 days, but it's every certain amount of time, it will double. That's what exponential, that's a feature of exponential growth. So we said in 12 days, it could go from 5,000 to 80,000. Does everyone see that?
Yeah.
That happens when the variable is in the exponent, like this, both of these. Okay? Then you get a doubling time, and then so if we have, and this was actually happening in China at that time, it was about 3 days. It was actually a little bit less than 3 days for a while. But let's say it was 3 days. That means that in just 12 days, the number of cases would go from 50,000 to 80,000. I'm sorry, from 5,000 to 80,000 in just 12 days, right? And then 3 days later, what would it be? Instead of 80,000, it would be 160,000. So just in 15 days in 15 days, it would go from 5 to 160,000. Okay? So, and that was happening for a while. And then the doubling time started to slow down. So it wasn't 2.5 days anymore. It was like 4 days, and then it was 5 days. So it wasn't actually growing exponentially anymore, because exponential growth means the doubling time is constant. So it's always 3 days. 3 days now, 3 days the next time, 3 days next, and so on. That would be exponential growth. So anyway, so that shows you how fast things grow when they're growing exponentially. Okay? One more example of exponential growth is, here's a story that I heard. I never did the calculation myself, but suppose you took $1 at the time that Jesus Christ lived. So in other words, 2,000 years ago, and you put it in the bank, whatever, and you got like a typical bank interest rate. Let's say, I don't know what the typical bank interest rate is. Let's just make it up, 2%. Okay, then how much would it be worth today? So when you get interest, that's also exponential growth. That's another example of exponential growth. If you get interest, you're actually, the way your money will grow is exponentially. Okay, so how much would it be worth if you took $1 and you put it in the bank 2,000 years ago? How much would it be worth today? So the answer is, it would be worth the amount of gold that fill 1,000 suns. So that shows you what exponential growth does. So if you just let the money grow exponentially, $1 would be worth the amount of gold that would fill 1,000 suns. Okay, so that gives you some feeling for exponential growth. Okay, let's go on. So anyway, populations grow exponentially. This is population growth here, and populations grow exponentially, generally speaking. And so they tried to model the actual population growth with this red line, and this red line is an exponential function. Does it fit perfectly, the blue dots?
No.
No, the red line doesn't fit perfectly the blue dots. It's just a kind of approximation of the blue dots. But you know, if we only use the blue dots, we have to work with this table. But if we use this model, we can work with a formula. So if you're satisfied with just working with the table, you can just use the table. But if you want to be able to work with a formula, then you're going to only approximate the blue dots with, or the blue dots with a formula, like with this red line. So this red line is this formula, even though it's just approximation, it's kind of useful because here, if I want to know what's it going to be in 2030, I can't really do that with this. You know, I don't really know what to do in 2010, in 2020, in 2030. I don't really know what to do. But here, I can just put it into this formula, put 2020 into this formula, and I'll get some approximation for what it's going to be. So, you know, we might prefer to have this approximation, even though it's not exactly right, because we can use it to make predictions about what's going to happen in the future, or to make some kind of prediction about what the population was right here, when we don't really know what it was, say in 1945. We only know 1940 and 1950, but here we could make we could use the formula to make a guess about what it would be. Okay, any questions about that? Okay, I think we were supposed to have a quiz now, so we're going to do that now. So it's in Manaba. I'll stop sharing my screen. And let's go to Manaba. Our Manaba website. And let's go to the tests area. And we're going to have a short quiz. Is anybody not there yet? Okay, so I will start now. It's a very short quiz. In fact, it's just one quick problem. So I'll give you, let me just see what it says. Okay. Oh, it's not as quick as I thought. Okay, so I'll give you 5 minutes to do this. So anybody not there yet?
Professor, I can see the quiz.
Cannot see the quiz, right?
Yes.
Yeah, okay, I'm gonna turn it on right now. Okay, so here goes. Okay. Okay, if you refresh your screen, you should see it there. Okay, you have 30 seconds. Okay, you have 15 seconds. Okay, did everybody submit your question? I like the guy dancing in the background there. What is that? Interesting. Okay, I'm gonna unpublish it now. Has everyone submitted theirs? Okay, very good. Okay, very quickly, we have one more topic to cover. And that is, let me share my screen again. That is for homework. Let's take a look at this. Okay, let's quickly take a look at this problem up here. So it says a piano manufacturer has a daily fixed cost of $1,000 and a marginal cost of $1,300 per piano. So we didn't really talk about this word marginal that much, but what it means is, in this context, it means the cost per piano. So we're talking about the cost in general, so we'll write it like that. Some books write it like this, total cost, but in our book they're using just cost, like that. So this means the cost per, the total cost, I guess, per item. And X is the number of pianos in this case. So what's the function here? Can anybody tell me? What's the expression for the cost function? So the fixed cost is $1,000. So that means no matter how many items we produce, the cost is going to be 1,000. If you do 0, 1, 2, or 100, it doesn't matter. So that's called the fixed cost. So we have 1,000 there. And then plus, for each piano we make, we have to, it's going to cost us an extra $1,300. So we write 1,300X. Does everyone understand that? Any questions about that? Okay, now let's go to here. So here we didn't talk about this yet. So we have the idea of a cost function, and we also talked about the idea of a revenue function. Maybe we did do this before, I forget. Oops, how do I do that? How do I move this thing? I can't, I guess I have to move it by hand. Okay, let me do that, sorry. Let's see, if I go to here and here. And then I can move it. Okay. And now if I go back here. Okay, so let's just quickly go over this. So we have, there, okay, and then here. How do I do this? Oh, I have to click here. Okay. Now, nope. How does this work? This is so annoying. I can't believe it. Okay. Okay. So, oh no, did it again. Why is that? Anybody know how to do this? Right. Okay. Maybe there. Okay. So we have this company estimates that it can sell 5,000 units here. The selling price will be $2 per unit. The variable costs are 20% of total revenue. Fixed costs are, well, let's just skip this problem. Let's just say if we have a cost function, so generally the cost function depends on X, on the number that we produce. So let me erase that, sorry. Okay, so it's going to, the cost increases. So it might look like that. What's this called here, this y-intercept? What's that called?
Fixed cost.
That's the fixed cost. The fixed cost is right there, the y-intercept. Okay, so this is the cost function. Now, the revenue function, let's say the revenue equals the price times the quantity. Let's say the price of this particular product is $100. So that it would be this. That would be the revenue function. Okay, so what's the y-intercept for this? This is the function. What's the y-intercept?
6,400.
No, the y-intercept is 0, right? There's nothing here. So there's no y-intercept for this one, okay? So the revenue, I'm not doing this here. I'm just talking about this. So the revenue is P times Q. So that means there's no y-intercept. What does that mean about the graph? That means it originates from the bottom, from here, from the origin. Right? Does everyone agree with that? But hopefully it looks like something like that. In other words, hopefully, eventually, so if you sell 0 items, your cost is going to be higher than your revenue because you have a fixed cost, but you don't have any, but revenue starts at 0. So the fixed cost is going to cost you money. But hopefully, as you increase the sales, hopefully your revenue will overcome the cost. Otherwise, you're never going to make a profit. So if it doesn't do that, you're in trouble. So hopefully it does do that. So the question is, where does it cross? And I think maybe we talked about it, I can't remember. That's called the break-even point. So that's the number of goods that we have to sell in order for the revenue to finally reach the cost. After that, once you get more sales, then revenue surpasses the cost, and then you're making a profit of this amount. But right here, the revenue equals the cost, then you are breaking even. So in the homework, you're going to have to do some problems to find the break-even point. Break-even point. Okay, so you'll do some of that, and you'll also do some homework on functions in general. Okay, that's all for today. Thank you for coming, and we will have some quizzes next week as well. If anybody has any questions, you can stick around, and I'll try and answer them. Otherwise, you can go. And stop.
Professor, can I ask a question?
Yeah, just a second. Want to stop cloud recording.